All right, we're going to finish up our one-dimensional worksheet with the combination questions, 13 through 16. If you notice, your teacher kind of made a mistake. Number 13 is exactly the same as number 1, word for word. So we're going to skip number 13 because we've already done that one, and I think it was pretty easy. So we're going to jump right to 14. 14, we have a track athlete runs 400-meter dash one time around the track in 53.6 seconds. Okay, so basically he started at one point, he's running around a track, ends up back where he started. His distance that he traveled is 400 meters, right? It's the 400-meter dash. What's his actual displacement? He ended up right where he started. So his displacement is 0 meters. Okay, and this is kind of that, how your teacher likes to trick you and ask you things. So when we say speed, what is his average speed? Let's write down his time here, 53.6 seconds, which is super fast. This guy's a great athlete. There's a person, didn't say a man, could be a woman running this. Okay, is equal to the average speed. So speed is question. Then the second part, this was A, it says velocity. So speed is equal to distance over time. So it's my 400 meters over my 53.6 seconds. Velocity is equal to displacement over time. So that's just equal to 0 over whatever. So 0. Excuse me. And on this first one, we have 400 divided by 53.6. And we get 7.5. So you can see how speed is different than velocity. Okay. 15. A bear dives into the water and begins swimming with a speed of 2.6 meters per second. So my initial velocity is 2.6 meters per second after 9 minutes. So my time is 9 minutes. We know we don't like minutes. There's 60 seconds in a minute. And so we're just going to multiply by 60 and get 540 seconds. And then he arrives at the far shore with a final velocity equal to 2.2 meters per second. And what was his distance that he traveled? Okay, you notice they didn't give me anything with acceleration, and so we're going to use one of these first couple, but they gave us instantaneous velocity, so we're going to use this second equation here. So this is 1/2 times VF plus VI times T. Okay, so we're just going to punch our numbers in there. So 1/2 VF is equal to 2.2 meters per second plus the 2.6 meters per second. And put that together times the time of 540 seconds. And let's see what we get when we do all that. 0.5 times 2.2 plus 2.6. And that times 540. And we get 1,296 meters that he traveled across. Pretty quick and easy. 16. 16 was a little involved. It had a lot of stuff going on. Let's see if we can get him up here. So 16, it said it's found that the position of a model airplane as a function of time is given for a portion of time by equation x equals 2t. So x equals 2 times t squared. Okay, I'm going to turn my paper over so I don't have to keep staring at number 15. So 16, x equals 2t squared. It says create a data table and fill in the missing x values. Okay, so we're going to have time, t, and this is going to be in seconds, versus position, x, and they don't tell me what the units are, so I don't know. Let's just call it feet, or meters, or whatever. I put feet. And so our first one, it says time, we're going to go from 0, 1, 2, and 3 seconds. Okay, and so my position, 0, is just going to be 0. 1 squared is 1 times 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. So there's part A. We have filled in the data table. Part B says plot a graph of this equation using the data. So let's plot my graph. Okay, so we'll call this time 0, and then 1, 1, 2, 3, 2, 1, 2, 3, 3. So this is my time in seconds, and then this is my position. We've said it, we're going to call it feet. We started at 0, and we have to come up with some. What are we going to make this? We'll make this 2, 4, 6, 8, 10, 12, 14, 16, 18. Ah, perfect. Okay, planned it. Okay, so at 0, 0, at 1, we're at 2, at 2 seconds, we're at 8, and at 3 seconds, we're at 18. So you can see we're starting to form an exponential curve there as we go out. So that's part B. Part C, from the graph, determine the average velocity during the 3-second interval. Well, average velocity, right? It's just a final velocity plus an initial velocity divided by 2. Or we have that wonderful equation that says that our average velocity is change in position over a change in time. And it said for the 3-second interval from 3 to 0. So my change in position, x final minus x initial over time final minus time initial. We'll pretend it's a change in this one. So the final position was 18, right? My initial position was 0. My final time was 3. My initial time was 0. So we get 18 divided by 3, or that would be 6 feet per second. So that's part C. Part D. Draw a tangent line at 2 seconds and estimate the instantaneous velocity. Okay, this would be, it's an estimate. So the tangent line is where we touch that line at one spot, right? So right about there, because if I move it any, I start to see more of the line. If I move this way, I start to see more of the line. So it hits one spot. And I would have to try to estimate what the slope is. So let's pick 2 points that kind of cross right on little dots there. It would cross right there, or we could go up to like this one. Okay, and so now our slope is equal to a change in the vertical, the rise, over the change in the horizontal. In this case, it's the delta x over delta t, because x is the vertical and time is the horizontal. So let's pick this point. So that was at 3, we were at 16. Okay, and then here we were at 2. So my position went from 16 to 2. My time went from 3. And my initial time is what, 1 point, it's thirds, 1.3. So something like that. So up here we're going to get 14, and this down here we're going to get 1.7. Let's see what we do when we get all that. 14 divided by 1.7. And I get 8.23. Okay, now is that perfect? Is that correct? It's an estimate. So you probably could have got anywhere from about 6 to 10 meters per second, depending on how you drew your line and which points you picked. Okay, any of those would probably be pretty good because it's just an estimate. We're doing the best we can. And the last part should say E. For some reason it says F. I think I deleted a part out. Is this plane going at a constant velocity? Well, we can tell it's not going constant velocity because the velocity changes at each point, right? Because if we look at our slope, the slope tells me velocity. Look, the slope there is much different than this, which is different than that. See how it keeps changing? So we're changing how fast we move. And so this would be no. That's what we can see. All good? That's it for the worksheet.